Okay, so today we're going to move into our half and double angle formulas. And as I was saying on Monday, we've just got more formulas that we can apply our trig foundations to. And now what these half and double angle formulas are going to allow us to do, particularly the half angle formula, is going to allow us to compute values of trig functions by hand on a broader set of angles. Instead of just having a reference angle of 30, 60, or 90, or 45, we can have things like 22 and a half, things like 15 degrees. So let me go ahead and first write off the formulas. And I guess we should put our little cheat sheet up, our reference sheet. So what are we going to be needing with our reference sheet? Let's go ahead and put our two triangles. So our 45-degree, and I'll put it in radians. Our 30, 60, 90. And we will be needing this guy, if not today, for on Friday for sure. A lot of these half and double angle formulas, the way we can phrase them, or at least the questions that use these formulas, you got to be careful about what quadrant you end up in. So we'll keep that diagram up there. Pythagorean identities and the even odd identities, all those still valid. I'm not going to write those. Hopefully you guys are getting used to using them when you need to. But the formulas for today, so let's go ahead and write those. The formula for cosine of 2x. So we have some angle x, and now I want to be able to, in some sense, reduce the argument here. So it's cosine of twice an angle. And if we can express that in terms of trig functions evaluated on the angle instead of twice the angle, we can make our lives a little bit easier sometimes. So cosine of 2x is equal to cosine squared minus sine squared. This is actually one of the easier ones to remember. I tell most of my calculus students that there's only two trig formulas you really need to remember, other than your reference triangles, but by calculus should be ingrained. The formulas you need to remember: cosine of 2x, cosine squared minus sine squared, will come in handy, especially once you get up in the Calc 2 and doing integrals of squares of trig functions. And then, of course, the Pythagorean identity. So cosine squared plus sine squared is 1. Cosine squared minus sine squared is a double angle identity. So that being said, we can find other formulas for this. So for example, cosine squared, we could convert those to 1 minus sine squareds. So 1 minus 2 sine squared of x gives us cosine of 2x. Or likewise, we could have converted the sine squareds to 1 minus cosine squared. And that'll give us 2 cosine squared x minus 1. So a lot of these double angle formulas and half angle formulas are going to have different forms. Sine of 2x is 2 sine x times cosine of x. And tangent of 2x is 2 tangent x over 1 minus tangent squared. So tangent, we could have taken the sine of 2x divided by cosine of 2x, done some fancy trig algebra to arrive at that. So I'll leave that as an exercise for you guys to try to check that. And then we also have our half angle formulas. So cosine of x over 2. So this is saying if I have half of an angle, maybe I can phrase it as equal to some sort of mathematical expression involving the original angle, it might make our lives easier for computational purposes. So what you can actually do is take these formulas here and solve for sine and cosine, respectively, in terms of the double angle, and then do a substitution. Again, I'll leave that for an exercise for you guys, and if you do that, you'll find that cosine is going to be 1 plus cosine of x over 2, and sine of x over 2 plus or minus 1 minus cosine all over 2. So the plus or minus comes about because you got to be careful where this angle lands. So you have to understand where the original angle is, where x is, and then where half of the angle is. So if x over 2 is in the first quadrant, say, we're going to want positive. But if x over 2 is in the second quadrant, in the second quadrant our cosine is negative, sine is positive. So just be careful on the signs with those guys. Likewise for tangent. Tangent has a few formulas. Because again, tangent of x over 2, we can just take sine divided by cosine. And so we will get plus or minus 1 minus cosine x over 1 plus cosine x. But you can also do some fancy trig manipulation and actually show that this is equal to sine x over 1 plus cosine x, or 1 minus cosine x over sine x. Whenever we're using tangent, I actually like to use one of these two more. And actually, I like to use this one the best. And why is that? Well, there's no plus or minus in these two, if you notice that. Here we need the plus or minus because we need to understand where x over 2 is originally. However, wherever x over 2 is, it'll necessarily dictate where the angle x, where twice that angle is going to land. And so in these two formulas over here, there is no plus or minus. Plus or minus is ingrained in the sines and cosines because sines and cosines themselves can be positive or negative. So wherever the angle lands, wherever twice the angle lands, it'll necessarily come out correct with the correct sign using these formulas. The other reason I like this one a little bit better than this one as well is because there's no sum in the denominator. We kind of like it when the denominator is factored or if there's just one term, right? Because I could write this as 1 over sine minus cosine over sine if we wanted to. We can split up the numerator in terms of the fraction. We can't do that here. So this one's almost a little bit simpler than all the other ones. So therefore, I try to use that one whenever we can. Okay, so those are the formulas. Keep that sheet handy. And again, on tests, quizzes, we'll give you all of these half angle and double angle formulas. We don't expect you guys to memorize these. I don't even memorize them off the top of my head. I memorize that one because that one's easy, but all of these ones, I usually either have to look up or derive from some of the other things I've memorized. So we'll keep this handy. We'll have even more formulas next week once we start the angle sum and angle difference identities. And again, those ones, they'll be similar to what we're doing today, just a little more complicated in some sense. And you won't have to memorize those. Okay, so let's do some examples. So we like our denominators of pi over 2, pi over 3, pi over 4, and pi over 6. We know how to compute anything with those denominators or some fractional multiple of those angles. So the numerator can change. So what's going to happen now if we take half of that? In some sense, we're actually not going to get too much more diversity in terms of the number of angles and number of denominators we can see as these fractions of pi. Because, well, what happens if I take 2 divided by 2? Or pi over 2 divided by 2 gives me pi over 4. Pi over 3 divided by 2 gives me pi over 6. So really we're only going to get, or at least start off, getting 2 more, namely pi over 8 and pi over 12, when we take these 2 angles and cut them in half. Okay, so let's take a look at pi over 12. And let's evaluate some of the trig functions. We'll try to do sine, cosine, and tangent. All the other ones, so secant, cosecant, cotangent, you essentially just use the first 3 formulas that we use, and you can always take the reciprocal once you've computed those to figure out the other 3 trig ratios. So how do we compute then sine pi over 12? What you want to do is write it as, let's do a little scratch work, as half of an angle. So pi over 12 is 1/2 times pi over 6. So when you factor out the 1/2 from the denominator, this known angle becomes the x. And when we look at our formula, so pi over 12 is half of pi over 6. We factored out that 1/2 there. And so we're going to use this formula where our x is pi over 6. So we have the square root of 1 minus cosine of pi over 6 all over 2. The plus or minus depends on the quadrant, but pi over 12 is in quadrant 1. So sine, the net result of this should be positive. So we're going to keep it just positive. Then we just compute. So you pull up your reference sheet. We need to compute cosine of pi over 6, which is going to give me square root of 3 over 2. And then all of that, 1 minus square root of 3 over 2 is divided by 2, everything under the square root. So if you're comfortable using these formulas and just plugging things in formulas, which some people are, some people aren't, especially if the formulas as they are can be a little complicated. The hardest part then comes down to simplifying this. So you got to remember all your algebra. How do we simplify expressions like this? The thing you want to do is at least get rid of any sort of compound fractions. We don't want a fraction within a fraction. So let's write this as a square root. Everything's under the square root 1/2. So I'm pulling out that 2 from the denominator times 1 minus square root of 3 over 2. And then just distribute the 1/2. Now, square roots under square roots are what they are. Unfortunately, there's not a nice mathematical way we can write that as like a 4th root or anything, not with a sum inside of it. So that's a good solution. The other thing you may want to do is find a common denominator for those. So we'll write the 1/2 as 2 over 4. So the other thing you commonly see is 2 minus square root of 3 over 4. And then because we have a square root, we can write the numerator. We have to keep the 2 square roots in there, but then we can take the square root of 4 in the denominator. So that's probably how the answers will look on tests and quizzes. Answers like this, though, for me, in terms of homework and written responses are fine. So what's going to happen if we try to compute cosine pi over 12? Essentially the same thing. Our formula is 1 plus cosine. The angle, the double angle, is pi over 6. And so we just plug it into the formula, and now we have to compute this guy. Cosine of pi over 6, again, was square root of 3 over 2. All over 2. And now everything's going to simplify essentially the same way if you follow the algebra here. The only difference is instead of this minus sign that we had in the sine formula, we just have a plus sign. So that should simplify to square root of 2 plus square root of 3 all over 2. And again, because of the angles in quadrant 1, we're just going to keep positive. So tangents, I'll leave to you guys. Let's try to get through some more examples. Let's do something with a pi over 8. And let's actually change the denominator a little bit. Let's do, or excuse me, the numerator. Let's do 7 pi over 8. And so for the sake of doing a tangent, let's go ahead and compute that tangent of 7 pi over 8. So scratch work, you've got to, again, recognize if the denominator is something we don't like, it's likely going to be a half angle, or it's at least half of something that we do like. So 7 pi over 8 is 1/2 of 7 pi over 4. And we like multiples of pi over 4. So this, again, 7 pi over 4 then becomes our x. And when we plug it into our formula, we have tangent of x over 2. Let's pull it up real quick. Tangent of x over 2 is one of these. And let's go ahead and use this guy. As I was saying, I think it's a little bit easier. I mean, these two, they both have sines and cosines, but here the denominator is easier. And usually when you got a bunch of fractions, when the denominator is easier, it's going to make your life easier. So 1 minus cosine over sine is our formula there. So our x is 7 pi over 4. 1 minus cosine of 7 pi over 4 over sine of 7 pi over 4. That's how we should evaluate this. So before we compute those, real quick as a mental check, 7 pi over 8, what quadrant is that in? Seven pi over 8 is in quadrant 2, right? It's smaller than 8 pi over 8 just by a little bit. So if it's in quadrant 2 and we're computing the tangent of a quadrant 2 angle, we should get a negative answer. And so we'll see how that comes out with our computations here. So 1 minus, what is cosine of 7 pi over 4? Reference angle is pi over 4, so we will have a 1 over square root of 2. However, where is 7 pi over 4? 7 pi over 4 is in the 4th quadrant, which actually makes cosine positive. So that one's going to be a positive 1 over square root of 2. Sine is just 1 over square root of 2. And, again, quadrant 4, got to remember that negative. And this is where this formula is going to be a bit easier for us, right? I don't have a 1 minus or a 1 plus in the denominator. We just have 1 over square root of 2 with a negative. So how do we simplify this? We can simply take the numerator times the reciprocal of the denominator. And without that, since there's no plus 1 or anything like that in the denominator, it's just one single term. Taking the reciprocal is pretty easy. Square root of 2 over 1, all we got to do. And so now when we distribute that, what do we get? We'll have negative square root of 2 over 1 times 1 gives me negative square root of 2. And then negative square root of 2 over 1 times negative 1 over square root of 2 gives us a plus 1. And so that, we can check, is this answer negative? So square root of 2, again, is about 1.5. So negative 1.5 plus 1 should give us about a negative 0.5. So all in all, a negative value, which is what we were anticipating based on the quadrant we were evaluating tangent in. Any questions? Okay, so let's do one more example with something a little more complicated. So these are just basic evaluations, basic use of the formulas. You'll get more practice with that on the IC. Give something with a little bit more problems to solve. So suppose we have that sine of theta is negative 4/9 and tangent theta is greater than 0. We want to find cosine of half of the angle. So there's a little bit more work we got to do here before just plugging and chugging. I have sine of the angle. I have tangent of the angle. If we try to evaluate cosine, at least as a first step, cosine of half the angle, first step we can write down the formula. We need a plus or minus square root of 1 plus cosine theta all over 2. Great. Well, that's a formula. That might get us 1 point on a problem. But what do we do from there? So we can kind of got to think ahead and just say, well, what do we need? We need cosine of theta. And then we also need to determine whether or not we need the plus or the minus. So I have sine of theta, and we have information about tangent of theta. We're not actually given tangent of theta. So we have to use all these trig problem solving skills that we've been developing so far to first deduce the information we need in order to plug that into the formulas, namely our cosine of theta. So one question we always want to ask is, where is the angle? So theta has a negative sine ratio, but a positive tangent ratio. So theta is in quadrant 3. Tangent, remember, is only positive in quadrants 1 and 3. And since sine is negative, it can't be in quadrant 1. It has to be in quadrant 3. So I know I'm going to have a quadrant 3 angle whose sine ratio is negative 4 over 9. So that's our theta. What is the adjacent side? Pythagorean theorem. So we will have negative 4 squared plus x squared equals 9 squared. So we'll get x squared is 81 minus 16, which is, what, 55? Or 65, excuse me. And then 65 is what? Looks like it's 5 times 13. So when we take a square root, we're not going to be able to simplify square root of 65. So we can just keep it as square root of 65. So we had to do a little bit of work finding the angle, or excuse me, finding the quadrant of the angle, and then finding the other sides that we're missing in order to compute our cosine. And now when we compute our cosine, cosine of theta, and we should be careful actually. Our x should be square root of 65. However, what's the sign on x? We're on the negative x-axis, so we actually want the negative square root in this case, negative square root of 65. So 1 plus negative square root of 65 over 9 all over 2. And again, a lot of the work of these problems is making sure you're simplifying this correctly. We'll have square root. Again, I always just like to pull out that 1/2 of the denominator. It makes the simplification a bit easier. And then when we distribute the 1/2, let me go ahead and write that on a new sheet. So we will have plus or minus 1/2 minus square root of 65 over 18. And that's not a bad answer. If we wanted to find a common denominator, we'll have 9 over 18, so 9 minus square root of 65 over 18. But in this case, that doesn't help us too much because 18 isn't the perfect square. So I still have to have that square root over both the numerator and denominator. And then the last piece, the plus or minus. We should only have one answer, right? Right now we have 2 written down. Do we want a positive or negative?
Positive.
So remember, our angle is in quadrant 3. So here's a trick you can do to solve and understand where these angles are. So theta over 2, theta was in quadrant 3. So if theta is in quadrant 3, it's going to be less than or equal to 3 pi over 2 and bigger than pi. So those are our bounds for quadrant 3, right? Pi to 3 pi over 2. And so if we just divide everything by 2, we get this expression, meaning theta over 2 is bigger than pi over 2, but less than 3 pi over 4. So 3 pi over 4 is right here. Pi over 2 is this angle vertically. So our theta lies somewhere in between there. In other words, our theta over 2 lies somewhere in between there. Our theta over 2 is in quadrant 2. Meaning that if I am evaluating cosine of theta over 2, what sign should we get? Should get the minus sign. So you can cross out the pluses and only keep the minus sign. Any questions on that guy?